Hello students, now let us review in-class exercise 2 to topic 17 on carbonyl compounds. Okay, so if you look at question 1, it's actually related to the chemistry of magnesium, and we know that most of the chemistry we are aware of is its ionic compounds, but magnesium forms a special group and also an important group of compounds known as Grignard reagents. Ever since this particular question came out in 2010 for A-levels, many JCs have set it in their school-based exams. So you might have seen it once in a while when you're doing some of these questions. Okay, after that they give you some history about the fact that it was developed by this French chemist known as Victor Grignard. Okay, and you warm it with a solution of ethane in dry non-polar solvents, and you will obtain a solution contains what we call ethyl magnesium bromides. Okay, so this ethyl magnesium bromides. Many Grignard reagents with different alkyl groups and aryl groups have now been prepared and used widely in organic synthesis. Okay, if you are pursuing a career or a degree in chemistry, you would have prepared Grignard reagent in your year 2. Okay, some university even let the year 1 students do Grignard reagents. So it has been so widespread, so popular, and so fundamental that any chemistry students will probably prepare Grignard reagents once in their lifetime, at least in the research lab. Okay, so you have typical examples of the use of a Grignard reagent in the 2-step reaction of ethyl magnesium bromide with propanones. In the process, you get a tertiary alcohol known as 2-methyl butane 2-ol. Yep, and then you notice from here that at first maybe you think that it's not something which is very familiar, but you realize that if I just color code propanones, just the CH3 group, which is over here, and then after that I'm going to color code the ethyl bromides, the ethyl group, right? You'll notice that it kind of like it's being nucleophilic added to the carbonyl carbon. Yeah. If you simply recall from what you have studied in the topic on nucleophilic addition, this actually looks very familiar. Yeah. And then if I'm going to color code further, you notice that the following steps, the MgBr is now being removed, and then eventually I'm going to get the hydroxy group out. In this case, I'm going to produce the tertiary alcohol. Yeah. So in our case here, the ethyl group behaves as a nucleophile. It might seem a bit surprising, but if I'm going to look at the structure, you'll notice that it will not be very surprising. Okay, so if I'm just going to sketch my ethyl group out in terms of the structures, it will look something like this, and then I have a MgBr. Okay, it's a sigma bond. There's no mistake here. And if you notice, it is sigma bond. The carbon is sigma bonded to magnesium, which is an element less electronegative than itself. So therefore, I expect the bond to be quite polar. Yeah. And usually carbon will take on a partial positive charge, but in this case, because it is bonded to an element less electronegative than itself, it will take on a partial negative charge, and that explains why it behaves as a nucleophile in nucleophilic addition. Okay, so now let us jump straight into part 1. What type of reaction takes place in step 1? I think we have already indirectly answered this particular question, because when we were drawing out the structure for ethyl magnesium bromides, we highlight that the carbon directly bonded to the magnesium takes on a permanent partial negative charge. So therefore it behaves as a nucleophile. So the first step is therefore nucleophilic addition. So I don't think it comes as a surprise to many of you. So there will be nucleophilic additions. Okay, then if we are going to move on to the next step, suggest the types of reaction that occurs in step 2. Yeah, so you notice that in step 2, right, before we decide what kind of reaction this is in step 2, I think we might want to discuss what might OMGBr looks like, or how will it look like. Okay, so you can have different perspective on how this looks like. It can be viewed as simply an oxygen sigma bonded to MgBr. So this is one perspective you can you can look at. Yeah, so if it's sigma bonded to MgBr, I think it should be quite obvious that the O will take on a partial negative charge, the Mg will be a partial positive charge. Yeah, and then in the course of the reaction, the OMg bond breaks, and then H is being added, so that's some form of protonation reaction. So you can view it as an acid-base reaction, or it can even be called a protonation reaction. But acid-base might make a little bit more sense. Okay, or you can even call this a hydrolysis, because any of such reaction where the O something bond breaks and then it involves water. Because how do we know it involves water? Because we were not told what exactly is used in step 2. Are we told? Let us take a look. Yeah, we were not told what happened in step 2, but because the byproduct is Mg OHBr, so it does make sense that probably water is being added. Yeah, so acid base works, and because water is being added, we can also view this as some form of hydrolysis reaction. Okay, so we can also look at step 2 as hydrolysis. Okay, or you can call it acid base neutralization. Okay, so both of this works. And then finally for part B, suggest the structural formula of the final organic products formed when I'm going to use this particular magnesium bromide. So this should be phenyl magnesium bromide, is reacted with ethanol in a similar two-step process. We are just supposed to draw the final organic product. So in this case, there are a few things we can do. This will be the so-called the aryl group being added. So the nucleophilic carbon is over here. So this is delta minus delta plus. Okay, so because we are adding it to ethanol, what we need to do is just to follow the whole thought process of what exactly went on above. Okay, so if it's ethanol, then I have a carbon here, bonded to a H, bonded to a CH3. Okay, then of course there will be a phenyl ring bonded to it, because the phenyl ring is the nucleophilic site, and then of course not to forget the alcohol being produced as well in the course of the reaction. Okay, then next we are going to look at part C. The Grignard reagents, this is propyl magnesium bromides, can be easily converted into a carboxylic acid by using carbon dioxide. Okay, so this is the nucleophilic sites. Okay, so we have a nucleophile over here, and then suggest a two-step sequence for this particular conversion and giving the structural formulae of the compounds involved. Okay, this might be a bit challenging, but we are looking at the production of carboxylic acids from carbon dioxide. So if you look at carbon dioxide, right, it can be viewed as a compound containing two carbonyl oxygens in the stricter sense. So with that, because there are two C-double-O, you expect a delta plus, delta minus, and then a delta plus over here. Oh, sorry, a delta minus over here. Yeah, so because we are looking at the ethyl group as like a nucleophile, so if I'm going to sketch out a mechanism, MgBr, so I expect a delta minus, delta plus. Yeah, so if it's going to be a mechanism, then it will be a nucleophile attack at the carbon bond, double bonded to the two oxygen, and then one of the pi bond will break. Okay, so we are just following the same thought process as above. Okay, and where we are adding to the carbonyl carbon of the carbon dioxide in that sense. Okay, so with that, then what I'm going to get here is I'm just going to draw out the ethyl group, sorry, the propyl group. Okay, and then bonded to a C, double bond O, and then you expect an O minus, but remember earlier on, the O is bonded to MgBr, so I'm going to just write it out as OMgBr. I'm just following what happens above. And then of course the next step is likely to be a hydrolysis step, so I'm just going to draw out the carboxylic acids. Okay, OH. Okay, and then MgOHBr. Right. Okay, so with that, let us move on to question 2. Okay, so for question 2, we have malic acid occurs in green apples and grapes, is often added to beverages and confectionery to confer a sour taste. So I have malic acid here. You notice that malic acid is a dicarboxylic acid. Okay, so it's a dicarboxylic acid. I'm just going to draw out color code the carboxylic acid functional group. Okay, suggest the reagents and conditions you use in a 3-step synthesis of malic acids from bromoethanol, identifying the intermediate G and H. Okay, so we have bromoethanol over here. Yeah. If I'm going to get malic acid, so I would expect the carbon where the carbon dioxide comes from, right? It's where I'm going to add in a cyanide functional group. Okay, because if I look at malic acids, right, there's a total of 4 carbons. So if I'm going to number the carbon, there will be 1, 2, 3, 4. Okay, then the portion which are structurally similar to the starting material, bromoethanol, this will take on carbon 2 with the carbon directly bonded to the Br, and then carbon 3 where it's the carbon bonded to one of the carboxylic acid. How do I know carbon 3 must be the C-double-bond-O? I think the clue given to us is that we have a carboxylic acid here, and it's directly bonded to a group bonded to a OH. So this seems to be similar to a nucleophilic addition step. Yeah, so with that, maybe I can predict that G is the nucleophilic addition product. So I'm going to draw G out first. Okay, I'm going to draw in blue. So G is going to look something like this. Okay, like that. So this is the nucleophilic addition product. So I'm going to have the CN here. Okay, CN, and then of course and the OH like this. Okay, and then what's going to happen next is that I'm going to number the carbon so that everything is in order. So 2, 3, and then this is carbon number 4. Okay, and then in step 2, I'm going to perform a nucleophilic addition. Sorry, a nucleophilic substitution. Remember from our halogen derivative, because the bromine is bonded to carbon number 2. So step 2 will be a nucleophilic substitution reaction using ethanolic KCN. So I'm going to write out ethanolic KCN. Heat. Okay, I forgot to write down step 1. So step 1 will be HCN, trace KCN, cold. Okay, so therefore compound H will look something like this: NC single bond, and then CN, and then an OH. Okay, and then what do we do for step 3? We are going to simply just hydrolyze the C triple bond N to give us malic acids. To perform hydrolysis, what we need to do is simply adding sulfuric acid, and then I heat it. Yeah, so what we're going to do here is acidic hydrolysis. Okay, so yep, we have completed everything, identifying intermediates G and H. Okay, next we are going to work on part B. We were told that when malic acid is heated with potassium dichromate, compound N is formed. So let us go back and take a look at malic acid. So when it's heated with potassium dichromate, we expect the oxidation of the secondary alcohol at carbon number 3. Yeah, so therefore I expect compound N's to look like this. So I'm going to have the carboxylic acid functional group. I'm going to draw it out first, and then just let me go back and take a look. 1, 2, 3. Yeah, so carbon number 3 will be the ketones, and then after that I'm going to have another carboxylic acid functional group here. So heating N, okay, so this is N. Heating N in an inert solvent for several hours produces P and a gas Q. Okay, so I'm going to heat this several hours. So heat several hours. Okay, I'm going to produce P with the formula C3H4O3 and a gas Q. Okay, so a gas Q, I'm going to just write it as gas Q. Okay, then both N and P reacts with 2,4-dinitrophenylhydrazine. Therefore, P must be some form of ketone as well. Compound P also gives a yellow PBT with aqueous alkaline iodine. Okay, so therefore I'm just going to write it out here also. Okay, so P gives a positive test with aqueous alkaline iodine and AOH warm, and then CHI3. Okay, and then we are supposed to suggest structures for N and P, and then use the information to suggest the identity of gas Q. Okay, the easiest way to go about working on this particular question is first let us calculate or just write out the molecular formula for N. Okay, yeah, so 1, 2, 3, 4, so 4 carbons, C4H, 1, 2, 3, 4, H4, and then O, 1, 2, 3, 4, 5, so O5. Okay, and then we are just going to compare with the formula of P. Okay, so the formula of P is C3H4O3. Okay, so if I'm just going to do a direct subtraction, I'm going to end up with CO2. Yeah, so from here, we can easily say that Q, the identity of Q, is therefore carbon dioxide gas. Okay, and later on in organic chemistry, you will learn that such a reaction is known as decarboxylation. Okay, so when you heat it, carbon dioxide gas is being evolved. So this is known as decarboxylation. Yeah. So with that, I don't know what is the best way forward, but maybe one way you can go about doing this question is, first you want to decide which is the carbon, which carboxylic acid loses the CO2, or breaks up and loses the CO2. It's a bit difficult for most of the H2 students because you do not learn about the mechanism for decarboxylation. So therefore, it is easier if we simply focus on compound P. Okay, so what can we do with compound P? With compound P, we can determine the degree of unsaturation, and because we know that it contains a methyl ketone group. How do we know methyl ketone group? Why not methyl alcohol? Well, as I said to you earlier on, we start off with most of the carbon having one of the highest oxidation state, either +3 or +2, because they are either carboxylic acid or ketone. So you can't be getting an alcohol for P. Okay, but nonetheless, let us try to calculate the degree of unsaturation for P first to confirm whether the chance of it being methyl ketone is very high. Okay, so the degree of unsaturation 2N plus 2, it contains 3 carbons, so that will be 8. Okay, minus 4 divided by 2. So in this case, it contains 2 degree of unsaturation. And we understand that for the 2 degree of unsaturation, it is likely due to number 1, a carbonyl group. Okay, so either a ketone or aldehyde, but it's likely to be ketone. Yeah, and it coincides with the fact that it contains a methyl ketone. Okay, so likely to be a methyl ketone. Okay, and then the 2nd degree of unsaturation is likely due to a carboxylic acid. How come I can be so sure that it's due to a carboxylic acid? Because number 1, if it contains a ketone, that will take out 1 oxygen, and then the remaining 2 oxygen must be part of a carboxylic acid functional group. Yeah, so because of that, I am kind of confident that it should be a carboxylic acid. Okay, so when we try to decipher the structure of P, we have to begin by drawing out a methyl ketone group. Okay, so this is a methyl ketone. And then if you again use the same way of problem solving, the methyl ketone formula is C2H3O, and then the structure for P is, the molecular formula of P, C3H4O3. So if I do a subtraction, I'll end up with CHO2. So from here, I can easily conclude that the carbonyl carbon must be bonded to a carboxylic acid functional group. Yeah, so the final structure will look like this. Okay, yeah, so that's how we decipher structures N and P from the information given. Yeah, so from here, you can sort of conclude that this is the carboxylic acid that gets removed, otherwise in a reaction known as decarboxylation. Yeah, as a little extension, I'm just going to showcase to you how does decarboxylation works. Okay, so it tends to work at a position where I can do a shift in the groups, so I'm just going to showcase to you. Okay, so right now over here, I'm just going to draw out the structure. So this is carboxylic acid, but maybe before I showcase to you the mechanism, maybe I just want to remind everyone that the mechanism is not in your syllabus, so do not get very upset over it or confused. Okay, so this is the carboxylic acid like this. Yeah, so basically for decarboxylation, I am going to remove this portion as CO2, so this portion will be removed as CO2. Yeah, so I'm just going to heat it. Okay, Yeah, so for decarboxylation to occur, basically you're going to push electron density 1 round. Okay, I think first of all, the OH bond will break. This is where I'm forming the CO2. Okay, and then I'm going to push this in, okay, to form a C double bond C, and then the CO pi bond will break towards the H. You can see that it goes 1 round, and maybe if I just draw it out like this, it might be a closed loop for you. Okay, so with that, I'm just going to draw the arrows, and then because the CO2 is being lost, okay, so CO2 is gone, and then the other product will look like this. It will be an alcohol, OH, and then a carboxylate acid. Yeah, so those of you taking H3, you will recognize this group to be quite unique. So this is known as an enol. Okay, so this is an enol, so ENOL. Why is it called an enol? Enol because it contains an alkene and an alcohol. So the alcohol group is bonded to an sp2 hybridized carbon. Yeah, with that, you might also recognize that phenol is also a form of enol, but it's a stable form of enol because of the aromatic phenol ring. Yeah, in general, enol is not very stable. Yeah, so it will undergo a kind of reaction known as a tautomerization reaction. Yeah, so maybe I should draw a longer arrow. So it will tautomerize to give you the ketone functional group. Okay, so in this case, I'm going to get back the ketone. Okay, so what exactly is tautomerization? So basically, it is just a shift in the position of the double bond. So instead of a CC double bond, it's now shifted to a CO double bond over here, and then because of the shift in the double bonds, the H at the enol oxygen must be lost, and then it must be gained by the original sp2 hybridized carbon where the CC double bond is originated from. Yeah, so this is a kind of isomerization reaction known as tautomerization. If you are interested in this, you can either check it out online, or you can ask your H3 friends, because your friends doing H3 should be very familiar with tautomerization. Okay, so with that, we have come to the end of our review to in-class exercise 2.